This is an IGCSE Edexcel paper. It's an exam talkthrough from January 2021, suitable for anyone sitting the IGCSE Edexcel in the UK and internationally. So starting with question 1. The boxes give some situations and some energy stores. Draw one straight line from each situation to the energy store that decreases for that situation. The first one has been done for you. A car moving horizontally and slowing down. That's to do with the kinetic energy decreasing. A ball falling towards the ground means that its gravitational energy store is decreasing. A nucleus splitting due to fission, that's nuclear. A stretched rubber band decreasing in length. Because it's a rubber band, it must be elastic. Energy is transferred when a filament lamp is connected to a battery. Which method of energy transfer takes place between the battery and the lamp? That is electrical. Which method of energy transfer takes place between the lamp and the surroundings? Now notice with the lamp, the whole purpose of a lamp is to give off light, so that's going to be light radiation. The diagram shows the apparatus used to demonstrate the existence of electromagnetic radiation just beyond the visible spectrum. Electromagnetic radiation from the sun passes through a slit and a prism. The electromagnetic radiation refracts through the prism onto the screen. 5 thermometers are placed in front of the screen. Complete the table to show the missing parts of the electromagnetic spectrum. Okay, this looks gross. Just be careful here. Remember with the EM spectrum, just before visible light comes infrared. And just after visible light comes UV. So complete the table to show the missing parts. What would P be? Well, we know that Q is red light. And remember, with visible light, starting from the longest wavelength, it goes red, Richard of York, orange, yellow, gave, green, battle, blue, indigo, violet. So because we're starting at the longest wavelength, we want the EM wave that is before visible light, has a longer wavelength, so that is infrared. For R now, because we've been given red, we've been given violet, we want to pick a colour that sits between that, so it doesn't really matter which one you pick. I'm going to go for yellow. And then, because violet is the last one, the one with the shortest wavelength, we then want the next part of the EM spectrum that has a shorter wavelength than the violet or visible light. So that is UV. Suggests why the lower part of each thermometer should be painted black. That's because black is a good absorber of infrared radiation. The equipment is left for a short period of time. The thermometers now show a higher temperature than before. State the part of the electromagnetic spectrum in this demonstration that would give the largest temperature increase. That would be, again, infrared part of the EM spectrum. The diagram shows 2 objects orbiting a star. Object X has a circular orbit around the star. State the type of object that has a circular orbit around a star. So the star could be our sun. What has a circular orbit around the sun? Well, that's a planet. Object Y has an elliptical orbit around the star. State the type of object that has an elliptical orbit around a star. You can see that very oval shape here. So that would be something like a comet. Object X completes an orbit of the star in 35 days. The radius of the orbit is this. Calculate the orbital speed. So you want the equation given on the equation sheet, which states that orbital speed is 2 pi r over t. Make sure you check your units. So that's fine, but this is a big problem because we need it in terms of seconds. So you need to take that 35, times it by 24 to get it into hours, times it by 60 to get it into minutes, times it by 60 again to get it into seconds. So we do 2 pi times the orbital radius, which we can see is 1.5 times 10 to the 11, divided by that large number we just calculated, which is our time period, to get a value of 310,000 meters per second. And that is to 2 significant figures. The diagram shows apparatus used to investigate how the pressure of a gas varies with temperature. The volume of the gas is kept constant by the flask. The volume of gas is a control variable. State why it is important to keep a control variable constant through the investigation. Have a look. We're interested in how the pressure of the gas varies with temperature. So it's very important that we only have one independent variable, because otherwise you'd have two if you altered the volume. The easiest way really is to say to allow a fair test, which I know they don't usually like, but it is the marking point here. The pressure of the gas changes as its temperature increases. The graph shows the results. Explain how these results show that there is a linear but not proportional relationship between the pressure of the gas and its temperature in degrees Celsius. So we can see it's linear. Why? Because it's a straight line, that graph. However, it's not proportional. Why? Because it simply does not go through the origin, and that's what a proportional relationship would show. Use the graph to determine the value for absolute zero. We need to take this line until it hits that x-axis, because absolute zero is when the pressure is zero. And what is that? Well, you can see it's minus 300 degrees Celsius. Lyra, shh. Explain how the pressure of the gas changes as its temperature increases. Use ideas about particles in your answer. So pressure increases as temperature increases. I really want you to rote learn this answer, because we now need to provide an explanation. We need to say that there are increased collisions between the particles and the wall of the container, and therefore a greater force is exerted between the particle and the wall. And if you're feeling fancy, you can provide an equation to back up your answer. Remember, the FAP equation is important here, which states that pressure equals force over area. It's always great to provide equations. In these physics explanations, the pressure of the gas is 112 kPa when its temperature is 35 degrees Celsius. The gas is heated to 340 degrees using some different apparatus. Calculate the pressure of the gas when its temperature is 340 degrees. Assume that the gas has constant volume. 4 marks. Don't panic though. It's P1 over T1 equals P2 over T2 is the all-important equation. It's very important that these temperatures are converted to Kelvin by adding 273. That's where all the mark allocations come from. So that becomes 308 Kelvin, and this is 613 Kelvin. We know the first pressure, it's 112. The first temperature is 308. We're after pressure 2. The second temperature is 613. So what is our pressure? Well, we do 112 divided by 308 and then multiply by 613 to get 220 kPa to 2 sig fig. The volume of the gas is constant in the investigation. Give the name of the other quantity that must be constant for the calculation to be correct. Well, you need to keep the same number of particles of gas. A student does an investigation to show how the velocity of a toy car changes when the car rolls down a ramp onto a table and hits a wooden block. The graph shows how the velocity of the toy car changes with time. So we have a velocity time graph, which means, remember, the area under the graph line is the distance travelled, and the gradient equals acceleration. Make sure you are happy with that. Calculate the distance travelled by the car during the first 0.4 seconds. So we know we need to look at the area under this graph line, but make sure it's the appropriate area. So it's actually here. And I'm actually going to call it area A and area B. So because that's a triangle, we're going to do half times the base, which is 0.2, times the height, which is 4.3, to get 0.43 meters. What about area B? So that's here, this distance here, which is 0.2, multiplied by the height again, which is 4.3. That's 0.86, and then add them together to get your full distance, of 1.29 meters. So that's from adding those two numbers together. Calculate the acceleration of the car between 0.4 and 0.45 seconds. We're looking for this acceleration here, so we need the gradient. So that's y over x, which is 4.3 over 0.05 to get 86. But it's a negative. Look, our car is slowing down here, so it's a negative acceleration, which is why we need a minus sign there. State the formula linking resultant force, mass and acceleration. We need this formula triangle from my auntie, which we can see means that force is mass times acceleration. The car has a mass of 0.13 kilograms. Calculate the resultant force on the car as it slows down. So we're after F. So F equals mass times acceleration. We know our mass is 0.13. Remember the acceleration we just calculated is 86. So to two significant figures, our answer is 11 newtons. A piece of soft material is fixed to the front of the toy car. Explain how this will affect the gradient of the velocity time graph after the car hits the block. So what will happen to this gradient? Well, I'm hoping you'll see that the car will be slowed down more, so therefore we'd expect a shallower gradient. So there is a shallower gradient, meaning a slower deceleration. And why is that? Because the time of the collision has increased. The diagram shows a ray of light travelling from air to glass. Use a protractor to determine the angle of refraction. So you need to use your protractor to find this angle here, and you'll find that it's 17 degrees. State the formula linking refractive index, which remember is n, angle of incidence, which is I, and angle of refraction, which is r. Remember it's n equals sine I over sine r. Calculate the refractive index of this glass. So we know that the angle of incidence is 29 degrees. The angle of refraction we've just worked out is 17. Pop that into your calculator and you'll get a value of 1.7. A glass contains some fizzy water. Bubbles of carbon dioxide form at the bottom of the glass and rise to the surface. The graph shows the relationship between the volume of the bubble and the pressure of the gas in the bubble. Describe the relationship shown by the graph. First of all, the fact that it has that negative correlation means that the relationship is inversely proportional. You could also say that as pressure increases, the volume decreases, but honestly, if you just use the words inversely proportional, you'll get 2 marks straight out. State the formula linking pressure difference, height, gravitational field strength and density. It is pressure difference equals height times gravity times density, which is given by rho. The depth of the fizzy water in the glass is 22 centimetres, so that is density, which remember was rho. There's your depth. We're being asked to find the pressure difference, so let's write that equation out again. Convert 22 centimetres to metres. Gravity, remember, on Earth is 10. There's our density. So our value is 2,400 pascals. Calculate the pressure of the gas in the bubble when the bubble is at the bottom of the glass. Here's your atmospheric pressure. So we know the pressure due to the fizzy water is 2,400. Effectively, we want the total pressure. So you want to add those two numbers together. So your value here is this, 103,400. When a bubble is at the top of the glass, the pressure of the gas in the bubble is equal to 101,000 Pa, and the bubble has a volume of this. Calculate the volume of the gas in the bubble when the bubble is at the bottom of the glass. Assume the temperature of the gas remains constant. We have a volume. We're after a second volume. We have a second pressure and a first pressure. So this is P1V1 equals P2V2. And this is why it's so important that I've labelled everything, so I know where my numbers are going. Sort out the left-hand side. Divide both sides by 103,400 to get 0.082 to two significant figures. A force called upthrust acts vertically upwards on the bubble. When the bubble is released, it accelerates vertically upwards. Draw two labelled arrows on the diagram to show the forces on the bubble as it is released. So we know that upthrust is acting upwards. It's told us that. Let's label it. What's going to be pulling the bubble downwards? Well, it's going to be the force of weight. And the third mark comes from the fact that that upthrust arrow is longer than the weight arrow, and I know why, because we've been told it's accelerating vertically upwards. So use all your clues to get those 3 marks. The diagram shows a bar magnet. Draw 4 magnetic field lines around the bar magnet. I am not very good at drawing these. There's the first one, the second one, third one, and finally the fourth one. And remember, the magnetic field lines always point from north to south. The diagram shows a loop of wire connected to the terminals of a voltmeter. Explain why the voltmeter reading changes from 0 when the magnet is moved near the loop of wire. This is the generator effect. So it's all about voltage being induced. So the reason for this is the wire cuts the field lines. Again, something to learn. Inducing a voltage. And that's why that voltmeter reading changes. The diagram shows 2 students holding a piece of string with a box attached. The box has a buzzer inside and can move along the string. The buzzer in the box emits a loud sound of constant frequency. The box moves away from the student A at constant speed. Explain why the sound heard by student A has a different frequency to the sound emitted by the buzzer. Doppler effect. This is really all about why ambulance sirens sound different when the ambulance passes. So if you think about it, the fact that if we look at that frequency of the wave, when the box moves away, its sound wave will be stretched. And therefore we have a longer wavelength, which means we have a decreased frequency. And remember, frequency and pitch are linked, so we'll have a decreased pitch. So believe it or not, you get a mark already for saying this is due to the Doppler effect. So recognising that Doppler effect gets you 1 mark in the bag. The speed, as we know, remains constant, but the wavelength has increased and the frequency has decreased due to, state the equation, wave speed equals frequency times wavelength. So think about it. If that number remains the same, that value has increased. By definition, that value must have decreased. This means that the sound's pitch has decreased, so it sounds lower. Uranium-235 captures a neutron and undergoes nuclear fission in a chain reaction. The equation shows a possible nuclear fission reaction. Calculate X, the number of neutrons released by this fission reaction. Count this up. Let's look at the mass number on this side. It's 236 in total. What's the mass number here? It's 232. So what accounts for this difference? Well, it's due to the loss of 4 neutrons over here. Describe what is meant by chain reaction. So remember, these neutrons collide with the uranium, causing its nuclei to split, releasing 2 to 3 neutrons, which go off and collide with other uranium nuclei, and the process continues. So nuclear fission causes the splitting of uranium nuclei. 2 to 3 neutrons are released, which are absorbed by other uranium nuclei, leading to further nuclear fission reactions. Iodine-129 is an isotope found in radioactive waste from nuclear power stations. It has a half-life of approximately 15 million years. A sample of iodine has an activity of 72 kBq. Show that the time required for the sample to have an activity of less than 5 kBq is approximately 60 million years. People get confused here. You end up substituting in too many numbers and therefore you can't find the answer. This is your final answer. So whatever working we do needs to arrive at a number that's approximately 60 million years. So here we are. We have 72 kBq. After 1 half-life, its activity will be 36. 2 half-lives and we're down to 18. 3 half-lives and we're down to 9. 4 half-lives and we're down to 4.5, so we're down to less than 5 kBq. So we know that 4 half-lives have taken place. If each one takes 15 million years, we therefore know that we need a time allocation of around 60 million years. So that is the correct answer, because look, it matches. Some radioactive waste from nuclear power stations has a very long half-life. Discuss precautions that must be taken when disposing of this radioactive waste. So how are we going to dispose of it safely? You need to use strong containers which don't rust, such as plastic ones. Make sure they're not buried close to drinking water supplies, as they could pollute. Secure the waste site. You do not want anyone breaking in and having access to that. Don't pick an area prone to earthquakes, because obviously the earth shaking could have massive implications for safety. A student uses this apparatus to investigate the force needed to pull a block along a ramp. State the formula linking work done, force and distance. So there's work done, force and distance, so we know it's work done equals force times distance. The student pulls the block 0.89 metres along the ramp with a force of this. Show that the work done on the block by the 26 Newton force is about. Do not put that number into your formula. That's what you want your final answer to be. So work done equals force, which is 26 newtons, times by distance, which is 0.89 metres, to get a value of 23.1, which is around the 23 joules, which we were expecting. The block has a mass of 1.3 kilograms and moves vertically upwards 0.11 meters. Calculate the increase in GPE. So you need this equation, which states that GPE equals mgh. We know the mass is 1.3, gravity on Earth is 10, the height is 0.11. We have a value of 1.3 joules. Explain why the work done to move the block along the ramp is greater than the increase in GPE store of the block. So why could this be problematic, moving the block along the ramp? Well, that could be due to friction, or the block may not be moved at a constant speed. The student suggests it is better to use a less steep ramp to raise the block through the same vertical height. Discuss an advantage and disadvantage of using a less steep ramp. So one advantage could be that you need a lower force to stop the block from slipping down. So there's your advantage. However, with a less steep ramp means you have a longer distance, which is definitely a disadvantage. So a lower ramp means a longer distance, which is therefore more inefficient. The diagram shows some apparatus used to find the mass of an object. 2 pieces of metal foil act as a variable resistor. Remember, a variable resistor looks like that. When more mass is added, the elastic string stretches and the small piece of metal foil moves to the right. Draw a circuit diagram for this electrical circuit. The variable resistor has been drawn for you. So our ammeter looks like that. Our cell looks like that. There's your regular resistor. So let's get drawing. There's our ammeter. Here's the cell. And then your regular resistor looks like that. Complete the circuit. Draw a voltmeter on the diagram to measure the voltage of the variable resistor. So handily it's telling you where it needs to go. Remember, a voltmeter is added in parallel. Explain how the voltage across the variable resistor changes if more mass is added to the elastic string. Now this is hard. Let's actually look at this picture here to try and understand what's going on. So if we increase the mass, what that does is it pulls that metal foil block this way, effectively increasing the length of the metal foil, and with that means that there's more positive ions and that they're conveying more resistance to those electrons trying to get past. So the crucial thing is, as that mass increases, total resistance increases, and then according to VIR, well, we know that the voltage from the cell remains constant. If that resistance value increases, by definition, our current value decreases. We now next need to consider what's happening at the fixed resistor over here. We've just said that the current's less. Because it's a fixed resistor, that resistance remains constant, meaning that the total voltage is decreased. And then based on that, what must have happened to the voltage in the metal foil, the variable resistor up here? It must have increased to ensure that the total voltage remains the same. That is a disgusting question, guys. Don't worry if you're finding it hard. So let's write this all. The student extends the investigation by keeping the mass constant and replacing the cell with a variable power supply. The student measures the current in the circuit for different voltages. State the independent variable in the student's investigation. So that is what they're changing. We've been told we have different voltages. Plot the student's results on the grid. Draw a line of best fit. So let's steal this table. Now the thing you're changing goes on the x-axis, which is why that's voltage. It's the independent variable. Make sure you include units. Here's our current. It goes on the y-axis. It's what you're measuring, the dependent variable. Be careful with your units. Now I've started to pick a sensible scale. What about these milliamps? We need to go up to 14. Now we're ready to plot. Here's our first point. And now we need a line of best fit. Cool, I'm quite happy with that. We've got a nice even spread.